We will now move on to the keynote speeches chaired by Professor Yukitaka Murakami of Kyushu University, who is Vice Director of I²CNER. Ladies and gentlemen, please welcome our first chairman today, Professor Murakami.
My name is Yukitaka Murakami, the Vice Director of I²CNER. It's a great pleasure for me to chair the session. The research of I²CNER covers multidisciplinary science field of hydrogen production, storage, fuel cells, transportation materials, and CO2 capture and sequestration. However, due to today's time schedule, we have selected only the 3 keynote lectures, and other related topics will be lectured in the afternoon sessions by principal investigators of our WPI. We have 3 distinguished scientists as the speakers for this session. I believe you can see the brief CV of the speakers in the separately distributed sheet. The first speaker is Professor Rob RITCHIE. Professor Rob RITCHIE is currently the head of Department of Material Science and Engineering, University of California, Berkeley. Today we have 2 department heads of the 2 top material science department in US, University of California, Berkeley, and University of Illinois. Professor RITCHIE is head of UCB, and Professor David Cahill is head of the Material Science University of Illinois. Professor RITCHIE was awarded the JSPS Fellowship more than 10 years ago, I think I remember that, and stayed in my lab at Kyushu University for fatigue and fracture research. I worked with him. He is a top scientist in the field of fatigue and fracture in the world. It is our pleasure that he joined our WPI program as a principal investigator. Title of his keynote speech is The Role of Hydrogen in Accelerating Crack Propagation in Steels. Please, Professor RITCHIE.
Where did you get that picture? Madam Chairman, Professor Murakami, Director Sophronis, ladies and gentlemen, it's a great pleasure for me to be part of the kickoff of this International Institute for Carbon Neutral Energy Research. One would be hard-pressed to find a more noble or more essential quest at this time in our history. One of the things that appeals to me about this whole approach is not simply that it's a world problem, a pressing problem of great importance, in fact, the ultimate importance in some respects, but this represents, from a scientific or an academic basis, a union we've heard of science, a union with education, but it's also a union of science and engineering. To me, in the world of research in science, nothing can be more noble than the union of science and engineering. Today, what I see in America is almost a partitioning of this. Because of, in many respects, people protecting their turf, the funding agencies in science have become more scientific, and the funding agencies in engineering have become more engineering. And it's left a sort of a vacuum in between. And that vacuum, in my opinion, is where research should be done. It's focusing on real problems, problems of engineering significance, and applying science to those problems. And that's what I²CNER stands for to me. It is that union of science and engineering. Now, in many respects, this is extremely important in the side of I²CNER that I would represent, and that is this question of the role of hydrogen in materials and what it does to materials. If we're going to have a hydrogen fuel society, we have to be able to safely conduct our business through whether it be pipelines for hydrogen, fuel cells, and so forth, without catastrophic failures. And that's where the engineering side and the science side become absolutely important. And one of these topics, of course, is what hydrogen does to materials and how it can affect the properties of materials. A good analog of this is to look at the problem of fatigue. Fatigue is the most important mode of failure. In fact, 80% or more of all failures that we see in society today are associated with fatigue. And nowhere is this more important than in the aerospace industry. We cannot solve the problem of fatigue, but we can control it. And that's what the aerospace industry has done. It's controlled fatigue. It knows how to deal with it. It knows it can't generate fatigue-resistant materials, totally fatigue-resistant materials, but it can control it. Now, hydrogen presents the same possibility. Many think we can find materials that are immune to hydrogen embrittlement. I don't believe that's necessarily true. So we have to control it. We have to know that materials suffer embrittlement from the presence of hydrogen, and we have to devise means of controlling that through engineering and scientific understanding. And that's a topic I want to talk about today, which is the role of hydrogen in accelerating fatigue, the most important mode of failure in our structures, and how hydrogen affects this. And this is not a particularly sexy material, steels, but if we're going to have a hydrogen structure, a hydrogen infrastructure, a lot of this is going to involve common garden steels. And we have to know how these materials can deal with the presence of hydrogen. Now, here in Kyushu University, as Petros Stefanos has indicated to you, there are probably the best facilities on the planet for looking at this topic. So what does hydrogen do? Well, many of you, of course, know this very well, but hydrogen is a particularly onerous entity. It is extremely mobile, of course, being small in its diffusion, and its presence can severely degrade the properties of all metallic materials. This is paramount in many different forms. Obviously, it reduces the fracture strength. The material becomes, in many respects, at least in some respects, more brittle. It can degrade the ductility of the material, how much strain it can tolerate before it fails. It can severely affect the fracture toughness, which is its fracture resistance. Typically, a high-strength steel in the presence of hydrogen has about 1/4 of its toughness than it might do if it was in the absence of hydrogen. And perhaps the most insidious but the most important form is it can accelerate the subcritical growth of cracks. And that's cracks that don't grow catastrophically but grow slowly over a period of time or numbers of cycles. Now, in the aerospace industry and the nuclear industry, the lifetime of components, be it a nuclear pressure vessel, a piping, a tail section of an aircraft, a turbine blade in an engine, is dictated by how long it takes cracks to grow subcritically until they lead to catastrophic failure. And one thing that hydrogen can do is dramatically accelerate this process of crack propagation. And the net result of that, if it's not understood or not controlled, are premature failures, severely reduced lifetimes, and catastrophic failures in situations which are perhaps unacceptable. So how is that achieved? Well, it's achieved by numerous mechanisms. There are numerous mechanisms by which hydrogen can affect the properties of materials. But in a sort of a broad brush approach, there are 3 primary mechanisms where we can see hydrogen playing a role. Now, just in terms of fractography, this is a typical high-strength steel in a hydrogen-free environment. You can see a lot of, it's called microvoid coalescence. The material tears apart around the inclusions or carbides in the steel, as this case is. In the presence of hydrogen, though, the fracture changes dramatically. In this particular case, it's not always the case. In this particular case, it leads to an intergranular fracture at fracture stresses that are a fraction of what they would be in the absence of hydrogen. So one of the traditional mechanisms of hydrogen embrittlement is associated with decohesion, that hydrogen collects in internal interfaces and leads to a reduction of the fracture strength in those interfaces. This has been particularly difficult to prove, by the way, but is one of the more recognized mechanisms of which hydrogen brittle materials. It has another effect associated with the fact that it can enhance local plasticity, and this is an effect which was first pioneered at the University of Illinois by Howard Birnbaum and subsequently with Petros Safranis, and leading to local instabilities associated with plastic flow. This is the brittle mechanism, this is the ductile mechanism. Many have felt that it's an either-or situation, but we now believe that these mechanisms actually operate in concert. And of course, in certain materials, hydrogen can form hydrides, and these are particularly brittle phase, which can then fracture. This is a problem in things like zirconium, titanium, and so forth. And this is also a mechanism by which hydrogen can accelerate cracking. So the presence of hydrogen can lead to lower fracture stresses, lower fracture toughnesses, but vastly increased subcritical cracking, leading to shortened lifetimes. And so taking a leaf from the aerospace book, we're going to need to know how hydrogen affects the velocity of cracks. We're going to need to have that information so we can then make safe and reliable predictions about how long components will last in the presence of hydrogen. And this is an absolutely critical aspect of the hydrogen economy, that we can do this. And the parallel, of course, is in the aerospace industry, where this has been done very effectively. Not necessarily for hydrogen, but for... So how do we do this? How do we actually... how do we generate this kind of information? Well, again, it's a marriage of science and engineering. There's a need to understand mechanisms. There's a need to understand how hydrogen can get to boundaries, how it may lower decohesion, or how it may affect the local instabilities associated with plasticity, and how it may be synergistic with other events that are taking place. In steels, of course, we know there's a segregation of impurity elements to boundaries. There is clearly a synergism between this type of phenomenon and the phenomenon associated with hydrogen. There's a need to use mechanics. We can understand these mechanisms and then embed them in crack-tip fields and make predictions, which is a form of fraction mechanics, when failure can take place. So that there is both the science and the fraction mechanics and the integration of those which are very important for the understanding of this problem. So how do we quantify this? Well, this is, of course, very well known to many of you in the audience, but some of you may not. How do we actually quantify how hydrogen can affect the fracture behavior of a material? Well, the approach is generally used here is called fraction mechanics, and it's a relatively simple approach. If you have a component which has a crack in it, and all components have cracks in it, and we have a certain applied stress on that crack, we can define something called a stress intensity factor, which is of the form I've grown here. This is K. It's a function of the stress times the square root of the crack length with some geometry factor in there as well. And this defines the intensity of the stresses and displacements ahead of that crack tip. And as such can be then used to correlate to the onset of fracture. We can correlate the value of this stress intensity to when fracture can take place. And we can also correlate this term to the velocity in which cracks can take. So it's a quantitative means of examining from a continuum perspective when and how fracture takes place. Now, in its simplest form, we talk about a critical value of K, which is known as the fracture toughness. That's when the component breaks in two or whatever. It's the catastrophic failure point. But that's simply the end point. If one wants to know how long a component may last, a hydrogen tank, a pressure vessel, a piping, one needs to know how long it takes any pre-existing crack, which inevitably will be there, will grow until you exceed this fracture toughness. And that's what subcritical crack growth is, and that's the essence of the prediction of life in most engineering components. And so we talk about when K values are less than K, cracking can occur subcritically. And in the case of hydrogen, there are two primary factors that are important here. One is, of course, fatigue. Fatigue is always important. And hydrogen can accelerate fatigue, as I'll show you in a minute, by a variety of different ways. But in the presence of hydrogen, cracks can grow subcritically. You don't even need a cyclic load. They can simply grow under sustained or monotonic loading. And so we have to encompass both those phenomena. And we talk about things called velocity K curves, VK curves. This is the velocity of the crack. In this case, it's fatigue crack, dA by dN, the rate of change of crack length with cycles, as a function of this stress intensity factor. And in fatigue, we talk about a delta K because the stresses vary over the cycle. And so it's important to be able to characterize these velocities in various different hydrogen environments and to quantify this in terms of a stress intensity. And these VK plots then become the basis of life prediction because we can integrate these plots from some initial crack size to a final crack size defined by the fracture toughness and predict life. Now, one of the unique aspects of Kyushu University now is these sort of plots are being generated for the latest generation of materials that will contain hydrogen, and in one very important aspect, at very high pressure hydrogen. If we're going to use hydrogen economy, we're going to have compressed hydrogen. There is very little data that on the velocity of cracks in steels or other materials in high pressure hydrogen environments. Now, my colleague Brian Summerday will talk about this afternoon because he has one of the few facilities in the United States to do high pressure hydrogen. There are, 11 within facilities here in Kyushu University. So this is a very, very important aspect of the work that will be done here. So my take-home message today is that there is a need to understand how hydrogen affects the properties of materials, and one critical aspect of this is how it affects subcritical cracking. We need to generate data in terms of the velocity of the crack as a function of the stress intensity. We need to look at this under sustained loading and under fatigue crack growth loading, and we need to be able to cope with how you integrate these things together. And one other thing I might mention here is that some of the ways that this has been done tend to suggest that high-strength steels can be very, very susceptible, and low-strength steels can be far less susceptible to the embrittlement of hydrogen. And I think that is a myth. I think if you look back, you'll see many, many examples where people have used lower-strength steels, and I'm talking about steels less than a gigapascal in strength, thinking that they are relatively immune to hydrogen embrittlement. And in fact, that is not the case. And it's come about because of a lack of understanding of how the experiments are done. So let me just quickly review some of how this is done. And this is work some of which I did many years ago, but which is being done now here in Kyushu to try to quantify this very important problem. This is what these VK curves look like. This is a VK curve under sustained loading. This is the stress intensity versus the velocity of the crack. And we get these sort of plateau-type curves. They tend to level off here because the cracking becomes limited by some chemical or transport process of hydrogen. And under fatigue, of course, we have the same sort of curves. Now, instead of dA by dt, this is dA by dN as a function of the stress intensity, the range of the stress intensity. So we have these two different types of VK curves, dA by dt, dA by dN, function of K as a function of delta K. Now, in fatigue, you can see they get rather complicated. They have a sigmoidal shape, but in presence of hydrogen, we get these accelerations. We get an acceleration due to hydrogen at low stress intensities, approaching a so-called threshold, and we get accelerations at higher stress intensities above another threshold, which I've called KT max. And in a high-strength steel, this threshold is the one we measure under sustained loading. And so this has led people to think that there may be a superposition of these types of behavior. This is the sustained loading, this is cyclic loading, and we can simply superpose this data on top of fatigue under a non-hydrogen environment and predict what's happening in fatigue in hydrogen. Now, mechanistically, there are a whole plethora of mechanisms that are important. There are transport mechanisms of how hydrogen get to the crack tip. There is oxide at the crack that has to be penetrated. There is the mechanics of how the hydrogen affects the fracture inside the material. be it some decohesion at an interface or a dislocation pile up against an interface. And if we needn't be gaseous hydrogen, we can generate hydrogen in an electrolyte just from the oxidation in water, for example. All these mechanisms are extremely complicated, and these mechanisms still need considerable work to be done on the scientific basis. But in terms of the engineering side, these are embedded into crack tips, and we can see certain patterns. As I said, we talk about what we call true corrosion fatigue, where the effect of hydrogen here is occurring primarily at lower stress intensities. And people talk about stress corrosion fatigue, where we get this sudden superposition, this sudden elevation of the crack growth rates in hydrogen. And of course, in most cases, we have both these phenomena. Now, how can we take care of this effect here? This is a rather interesting phenomenon which has been known for some time, is that we can generate superposition. This is the rate of growth of a fatigue crack, dA by dN, delta, this is the crack growth rate versus the stress intensity. There we have the effect in air, and then we put it in hydrogen, and we get this sudden acceleration. And this can be basically achieved by superposing this data onto the fatigue data. But there's things we have to think about here. This is K, and this is delta K. So where this superposition takes place on this axis depends on the relationship between the cyclic and monotonic loads. The so-called R ratio, as sometimes it's told. And in this axis, we have dA by dt, and this is dA by dN. So the superposition in this direction depends on the frequency of loading. And so depending on the relative frequencies and the load ratios here, this superposition can take place at different points in the horizontal and vertical axis, but is in a very predictable fashion. So you can do this superposition in two ways. You can superpose the monotonic and the cyclic loading in series, or you can superpose it in parallel, depending on whether your two processes are simultaneous or are competitive. And I won't go into the details of this, but in high-strength steels, this is a very predictable process. This point at which you get this superposition, you can measure under sustained loading as the sustained load threshold. Very nicely cut and dry, and you can generate a good understanding. And this is what the data looks like. This is data on a martensitic bainitic steel. It's a pressure vessel steel. I haven't talked about this lower effect. I'll talk about this a little bit later. There's another effect here, but you can see the superposition here of data in hydrogen. This is in air. If we have hydrogen sulfide, of course, we get higher fugacities of hydrogen, and this leads to faster crack growth rates. This is in pressure. Now, this data was taken some time ago, and here we're dealing with the same superposition. This is basically air. Superposition in low-pressure hydrogen, which would be typically about a tenth of a megapascal. And at the time I looked at this, we had data at 7 megapascals. We got a much higher rate of crack growth in high-pressure hydrogen. 7 megapascals. The facilities here at Kyushu can do tests at 120 megapascals. Now, there's lots of data in the literature on hydrogen brittlement and how hydrogen affects crack growth, but there's very, very little data at these very, very high pressures. So from an engineering perspective, information on how cracks grow in high-pressure hydrogen, which reflects the reality of a hydrogen economy, is critical, and that's taking place here. I think probably this is the only place it can take place. There are very few facilities outside of Japan. And if we look at the load ratio, looking at different load ratios here, the details aren't too important, but you can see this superposition point now is shifted along the delta K axis and simply reflects the balance in the cyclic versus the monotonic loads. So this is, although we lack data in high-pressure hydrogen, we understand this process, and this can be used to generate these kind of so-called VK curves, which then become the basis of prediction of life for a given component. Now, there is another effect that's interesting, by the way. If you look at lower delta Ks, you see hydrogen takes place, also accelerates crack growth down here. And what's interesting, in these sorts of steels, where the mechanism is primarily decohesion related, the hydrogen-assisted cracking here is intergranular, but down at these lower delta Ks, it's not. It's transgranular still. And in fact, these lower growth rates are very important because they can dominate a life prediction calculation. Now, the complexity here gets very large, and one of the effects that we deal with down here is that not so much that hydrogen accelerates crack growth, but air can decelerate crack growth. In a moist environment, you form oxides at the crack tip. And at these very low growth rates, the opening of the crack, the so-called crack opening displacement, can be fairly small. And these oxides then can wedge the crack. The analogy is if you're talking and I put a donut in your mouth, you're less able to open and close your crack. Doesn't seem very scientific, admittedly, but it's a very potent mechanism which basically reduces the growth of cracks at these low levels. So the complexity of mechanism here is important. There are different mechanisms here, but from the engineering perspective, we need to be able to document how these data change and use this as a prediction of life. Now, there is one final point I want to mention here, is that this approach of superposition has been around some time and works extremely well with high-strength steels. But if we go to a low-strength steel, and low-strength steels are still used in a tremendous amount in engineering because they have higher toughnesses and are less prone to fracture. Below about a gigapascal, if we try this approach, it doesn't work. In this particular material, this is a lower strength 2¼ chrome moly steel, the stress corrosion, or the sustained loading threshold in hydrogen is at 85 megapascal root meters. It's about here. So many people have thought, okay, these steels are relatively immune to hydrogen embrittlement. If I have stress intensities below this level up here, I haven't got to worry. But if you do those experiments in fatigue, and most structures see cyclic loading, lo and behold, you get this same effect, this sudden acceleration, but at much lower levels than the stress corrosion, than the sustained load cracking. If you did the test under non-cyclic conditions, you'd have to have a K up here before you see hydrogen embrittlement, but under cyclic loading, it occurs at much lower levels. And the point is that this is the same sort of stress intensities you see in high-strength steels. So low-strength steels are as susceptible to hydrogen embrittlement under cyclic loading. But you wouldn't realize that if you were looking at under non-cyclic conditions. Now, why is that? And the reason is that in these lower-strength steels, the crack tends to blunt. And in blunting, it forms an oxide film, and it gets more difficult for hydrogen to penetrate that. But of course, that's a rather artificial situation, because in reality, there's always cyclic loading. And the cyclic loading then keeps those cracks sharp and enables the same phenomenon to take place as you would see in a high-strength steel. So let me conclude by saying here, I've tried to look today at one aspect of hydrogen which is of real great importance to society, and that's the fact that hydrogen degrades the properties of materials, making them more prone to fracture and making their lives much shorter than one might predict. And this is where the engineering side of this particular center becomes important, and one area where there's a desperate need for new data at high pressures, which are typical of that we're looking at in the future. And that's where KUSU is going to be absolutely critical. I've talked about how there are different effects at lower growth rates versus higher growth rates, and the need to look not simply at the final fracture, but at the question of subcritical cracking. I've looked at how higher strength steels can show this effect very, very obviously, but it's also present in low strength steels. And in general, how there's a need here to fuse the understanding, the scientific understanding of how hydrogen affects materials with the engineering need for actual data which can be used to predict the life and ensure the safety of our components that contain hydrogen. Thank you very much.
Thank you, Professor Ritchie, for your excellent 50% introductory and 50% very scientific lectures. Audience might be scared with the hydrogen effect on fracture, but we have to solve this problem. And today we have prepared official discuss at each keynote lecture. And for this keynote lecture, we ask Professor Kondo to make some questions. Yes, Professor Yoshiyuki Kondo of Kyushu University.
Thank you for your interesting lecture. I have a couple of questions. One is specific and one is general. The first one is, I've been wondering whether local plasticity is still concerned with the intergranular cracking or not. What is your idea?
I think it's of course a very good question. I think in early days one tended to think that these two mechanisms, the decohesion mechanism, which is brittle fracture, and the help mechanism, which of course is ductile fracture, were sort of mutually exclusive. They were two different phenomena. But I think now that we can understand that they're two sides of the same coin. Professor Pisaranis and myself have done some recent work where we've tried to embed a fracture mechanism for hydrogen inside a crack tip field and do a statistical model of this. And one of the things that came out of this is the local mechanism by which hydrogen affected the fracture, the rate-limiting step, so to speak, was a union of both the dislocation pileup, the health mechanism, and the resulting decohesion that it caused. So I think it's practically impossible to separate these two mechanisms. They are both part of a similar process. So I agree with you wholeheartedly that you can't ignore one at the expense of the other. And I think they act in concert in most situations.
All right, thank you. And the second one is general. You talked about a lot of topics in wide range. And could you give me a suggestion? What should be done more from now on for the safe operation of hydrogen?
Again, it depends on your perspective. From the point of view of the integrity of components, the reality is you're going to have a hydrogen infrastructure, you're going to have pipelines and so forth. One has to have the data. One has to have data on how hydrogen affects the velocity of cracks, the toughness and so forth in realistic hydrogen environments, which is high-pressure hydrogen environments. One can't wait necessarily for all the scientific understanding to be at the same time. Yet I think at the same time, from a point of view of a more fundamental perspective, one needs to understand how hydrogen affects this. But I think if you take fatigue as a good example, the aerospace industry couldn't wait for us to find how fatigue cracks actually grow fundamentally. There's a desperate need for that data up front. But you'd like to have the fundamentals there as well to provide some realistic understanding and a basis for extrapolation for long lives and so forth. But I think, in answer to your question, the most important thing is to have that engineering data in realistic environments, and that's what's happening here in Kyushu in that regard.
Thank you, Professor Kondo. And, his first question is very scientific. We always argue about the model, okay? But we have to we need to solve this, okay? And thank you, Professor RITCHIE, again.